Okay, so we were looking at what it means to be a continuous function. There were certain conditions that had to hold to be continuous. First of all, to be continuous, let's say at x equals c, we said that f of c had to exist. We have to show that the limit as x approaches c of f of x is equal to some value L, and the limit as x approaches c of f of x, f of x is equal to f of c, which in this case would be L. In order to show something, a limit exists though, we were talking about you have to show that the left-hand limit and the right-hand limit approach the same value. And so this was just to show that something was continuous at a value x equals c. And so when you have piecewise functions, we have to be careful when you're changing equations. Maybe let's look at number 24. And so first of all, the first function, x squared plus x minus 12, it's a polynomial. We talked about polynomials being continuous everywhere. And 3 minus x, the second equation, is also a polynomial. But because we're switching equations at x equals 1, we need to make sure that there's no jump there and that the same values we're going to get. And so if we look at the limit as x approaches 1 on the left-hand side, so I can denote that with that negative, of f of x, this would equal, well, the left-hand side, this is when x is less than 1. If x is less than 1, that tells me I'm using this first equation. So I'm looking at then the limit as x approaches 1 on the left is using the equation x squared plus x minus 12. We can use our limit rules, and we can just, because this is a polynomial and it's defined there, we can just go in and plug it in. So we have 1 squared plus 1 minus 12. So 1 squared is 1 plus 1 is 2. 2 minus 12 gives us negative 10. So now we want to look at the limit as x is approaching 1 from the right-hand side of f of x. Well, if we're coming in on the right-hand side of 1, that means that this is a value which is x is going to be bigger than 1. And since x is bigger than 1, we're going to use this second equation. So limit as x approaches 1 on the right, we're going to use the equation 3 minus x. Again, using limit rules, we can just go in and plug in. So we have 3 minus 1. This gives me 2. So graphically, the left-hand side and the right-hand side are not the same. So the limit as x approaches 1 of f of x does not exist. So right there, that is one of the conditions that fails for it to be continuous at a value. Just so that we can review it, let's look at, in this case, I'm going to change this. It will be easier if I change that little thing to f of x instead of h of x. But if we looked at what is f of 1, well, you have to look at it, what equation that holds for. Well, when x equals 1, it tells us to use actually the first equation. And so in here, we just go in there and plug in 1 wherever we saw an x. So we have 1 squared plus 1 minus 12. Which we saw before was 10. So earlier we talked about the different types of continuity, or where it could, if it's not continuous, discontinuity. So there could be a jump discontinuity. There could be a discontinuity that happens because of an asymptote, which we'll talk about in the next chapter, looking at rational functions. Or we could have what is called a removable discontinuity. So looking at these piecewise functions, and I'm not going to do all of them, maybe we can do 2 of them. We have to be worried about where it's undefined. So here, this last one, h of x, we use the first equation only when x is not -2. And then if x is equal to -2, then we use the second equation. So really what's happening, x equals -2, it's undefined in that first equation. And so looking at this, we want to look at the limit. Actually, what do we want to do? Yeah. As we want these 2 values to be the same in order for it to be continuous. So we want the limit as x is approaching -2 on the left of h of x to equal the limit as x approaches -2 on the right of h of x. So let's see what's happening when x is equal to -2 here. So h of -2, we're going to go into the second equation and we're going to plug in -2 wherever we see an x. So here we have 3 all times -2 plus k. So this is equal to 3 times -2 is -6 plus k. Okay, we're going to come back to this in a minute. Well, our limit, we need to find the value of k so that we're pretty much filling in a hole. If you looked at this equation, 3x squared plus 2x minus 8 all over x plus 2. Let me just call. This is, let me just call this y. We said it was undefined when the value makes the denominator equal 0. We're going to have the vertical asymptote if it doesn't also make our numerator equal 0. So I'm assuming, or I'm believing, that this factors. And one of the factors is x plus 2. Let me just look at this and make sure. I'm believing that this is probably going to factor as this. This is 3x squared. This is a positive 6x minus a 4x gives me my middle term 2x and -8 all over x plus 2. And so when I looked at the limit here, as x is approaching 2 on the left, well, I'm basically using this equation. And if we saw that and we plugged in 2 in there wherever we saw an x, we're going to get our -2. We're going to get the indefinite form of 0 over 0. That, remember, didn't tell us anything. That told us that we had to go back and kind of manipulate it. I kind of manipulated it already for us and factored it. And so now if we go back and we plug in this -2 wherever we see an x, we would get three all times -2 minus 4. So we get -6 minus 4 or -10. So in order for this to be continuous, this has to equal h of -2. So in order to be continuous, oops. We know that the limit as x approaches -2 of h of x has to equal h of -2. I can justify too that this is what my limit's going to equal either direction, because when x is bigger than -2, and I look at this coming in on the right-hand side, I know that that's a value of x which is bigger than -2, so that tells me to use this first equation. Again, I would get 0 over 0 in determinant form. I'd have to factor it, simplify. And so really I know that the limit as x approaches -2 exists, and it's -10. And to be continuous, the limit has to exist, we just showed, and it has to be equal to h of -2. So we know that this piece right here, which we found to be -10, has to equal this -6 plus k. So k, we can add 6 to both sides. Then we know that k then is -4. So we just made it where we had before an open circle. And then we figured out what k would have to be for this equation to close that circle when x was -2. Any questions on that? Let me just see what other ones we have. Let's look at 26, because that has k in both of them. And let me just kind of pause for a second if you need a chance to finish writing. Okay. Okay, so let's look at 26. It says to find the value of k that makes this function continuous. So the only problem that we're going to have is at 3. And so let's look at the limit as x is approaching 3 on the left-hand side. So if we're approaching 3 on the left-hand side, that tells me that it's a number that is smaller than 3. And this number smaller than 3 or equal to 3, we would look at this equation x cubed plus k. So we want to go in there, wherever we see an x, we're going to plug in 3. So we have 3 cubed plus k. And so 3 cubed is 27 and plus k. We want to look at the limit as x is coming to 3 from the right-hand side. And this is values where x are bigger than 3. And so that tells me I need to use this second equation. So kx minus 5. So this is equal to k times x, which is 3. So k times 3 minus 5. So this is equal to 3k minus 5. So in order for the limit to exist, these would have to be the same. And we're trying to make it continuous, so the limit has to exist. So we know for the limit as x is approaching 3, our function is actually g of x to exist. And then we know that this 27 plus k must equal this 3k minus 5. So we got a linear equation, we need to solve for k. Want to get terms with k to one side of the equation, constants to the other. So let's subtract 27 on both sides, and let's subtract 3k on both sides. So I got k minus 3k is negative 2k equals negative 5 minus 27, that's negative 32. Divide both sides by negative 2, we get 16. So g of x, k has to be 16. And our equations would be x cubed plus k, but k was 16, so plus 16 if x is less than or equal to 3. And then our second equation is k times x, or 16 times x, minus 5 if x is bigger than 3. If we looked at this, g I don't want you. G of x, what was I going to say? G of 3 is equal to, that would tell me to use this first equation because really in that it follows through. This is equal to 3 cubed plus 16, which is equal to 27 plus 16, which is equal to 43. If you plugged in 3 into the second equation, you'll notice that you also get 43, which we wanted because we have to get the same number on the left and the right. 16 times 3 is 48. 48 minus 5 is 43. Okay, so we found the value of k and made that removable discontinuity. We found k to make that continuous there. Let me just look real quick. I feel like that we actually did go through more of that stuff. Now looking at this, the limits involving trigonometric functions. We started, I noticed I did one back up here with a sine. And so we can do that same. We have a rule with compositions. Let's see, so let me just pull up another problem. So let's look at, what about the limit as t is going to 0 of the function cosine of, and this is rational, so in the numerator you have just a pi, all over, in the denominator we have the square root of 19 minus 3 secant 2t. Okay, so cosine function, that is continuous everywhere. Only problems that we're going to worry about is when that denominator is equal to 0. And secant is actually a 1 over cosine, so we might have some problems there. But let's look at this and plug in and go in, and wherever we see a t, we're going to plug in 0. And so if we look at this, this would give us back cosine. Actually, let me just use the rule. So this is the same thing as cosine of the limit t goes to 0 of pi all over the square root of 19 minus 3 secant 2t. So the rule says then that we can look at the limit of a rational function. We can look at the limit of the numerator all over the limit of the denominator. And I'm not going to actually write that piece out. So this is the same thing as the cosine of. So if we go back in here and we plug in 0 wherever we see a t, we have, well, limit as t goes to 0 of pi is just pi all over. Basically, I can take the limit of the square root and then the limit of what's underneath. So this is 19. Limit of a constant is a constant, minus 3 secant 2 times 0. So let's just reduce that. And so we have cosine of pi all over 19 minus 3 secant of 0. Remember, secant can be rewritten as cosine. This is 1 over cosine of 0. Cosine of 0 is 1, so 1 over 1 is 1. So 3 times 1. And I still, underneath the square root, is that 19 minus 3 times 1. So this gives me cosine of pi all over 19 minus 3, that's 16. The square root of 16. Square root of 16 is 4. So we have cosine of pi fourths. Cosine of pi fourths is root 2 over 2. Okay, so let's jump into rational functions. Just